received the very prestigious Fulbright Nehru Academic and Professional Excellence Fellowship from United States India Education Foundation. We congratulate Dr. Mukesh Kumar for crossing such great milestones within a short span of his career. So with this brief introduction, I hand over the session to our resource person. Over to you, sir.
Thank you, Pragya. And I accept your flower.
Thank you, sir.
Slides are visible.
Yeah, visible.
Okay, so I have about 1 hour, right?
Sure.
Okay. Okay, so good afternoon, everyone. My name is Mukesh Kumar, and Pragya, thank you very much for kind introduction. So today I'll discuss and share some results from our lab. So if you want to know more details about our lab and our research area, please do scan that, and it will lead you to our research website. So belongs to Department of Physics, IIT Ropar, and thanks Pragya to inviting me here. So first of all, I would like to start with the sincere acknowledgement. So I would like to acknowledge Solar Research Energy Initiative Series from Department of Science and Technology, BRNS India, SERB, DRDO, and IIT Ropar, who help us to establish this lab here in IIT Ropar. So this is the overview of our research that we are doing here. So we are working on functional and renewable energy materials here. And what we are doing, so you can see that we are working on the flexible and indium-free transparent connecting oxide materials, where we are trying to correlate the growth kinetics, material performance, and optoelectronic properties of the material. And I'll able to convince you that we are able to utilize the material that we are developing in one project to the different projects. So it is kind of a joint development for the materials as well as the devices. We are working on 2D materials like MOS2, BTS2, and different other materials for gas sensors and broadband photodetectors. We are also working on solar blind photodetector. So if you see that we are working from NIR region, like starting from 1550 to all the way to 250 nanometers. So that covers entire visible NIR and UV region. And we are also working on earth abundant solar cell, that is copper, zinc, tin sulfide, and selenide solar cells. So this is the presentation I'll discuss. So I'll just give a brief about the energy roadmap, why we need to go for this renewable energy. So if you see that the data actually is coming from International Energy Agencies, then this is the current scenario. So that is like in 2011. So that is a energy, if we are utilizing that energy, and then how much that energy source coming from the different, like the coal, so that the black color actually represent the coal and the oil and different resources. And you can see that from this entire energy, the very small fraction is coming from the renewable energy or the variable energy that we call is from the wind and the solar. Now, if you continue with this same projection and you keep utilizing that, there's fossil fuels and other sources, by keeping 20 or 30 years, then what will happen? So this 6-degree scenario, so that means the earth temperature may rise to 6 degrees centigrade by 2050. And that is actually is kind of devastating. And up to that, so if you are going to be increased by that, then about 27% will be the total renewable energy, and the variable energy is only 8%. On the other hand, if you want to have the 2-degree scenario, that means if you want to have the global temperature to be increased by only 2 degrees centigrade, then what we have to do, we should have the total energy consumption and the production about 65% that should come from the renewable sources. Or there are other scenarios where we can have the temperature which is the same as today, and then we can have the same temperature. So not only we have to work on the renewable energy sources, but also we have to capture whatever the carbon dioxide present in the atmosphere. And there are a lot of research activities going on in this direction. Now, I was told that there are a few students also in the audience. So let me go a little bit basic about that, since I'm going to discuss about the solar cell and different materials. So let me tell what are the materials qualified for solar cells, because the basics of the solar cell is like we have a material, and that material absorb the light, and then that light is being absorbed by the material is converted into the electrical energy. So we are converting the light energy into electrical energy. So here is the free electron model. So where we have this free electron, suppose we have electron that is free, then how this energy and the momentum actually look like. But if you keep this electron, same electron inside the material, and the material is solid, so we have the arrays of the atoms. So these are the one dimension arrays of the atom. And if you allow this electron to pass through these potentials, so then what will happen? There will be a band formation, and there will be the bands of the allowed energies and separated by the energy gap. So this is the energy gap, and then these are the allowed energies. So then we have understood that there are the energy bands which is separated, okay, by the unallowed. So that is the energy gap. And we need a semiconductor, okay. So we need a semiconductor to absorb that light. So we know that the light is coming which has an energy h nu, where h is the Planck constant and mu is the frequency. So when this photon is shining, we want that photon should be absorbed by the material, but this photon will only be absorbed if the energy of the incident photon is nearly equal to the band gap of the material. So how we define the band gap? So this is the band gap. So this is the EK diagram. And then we have the band gap is defined as the minima of the conduction band and the maximum of the valence band, and what's the energy separation between them. So this is the fundamental band gap of the material. Now, if this minima of the conduction band and maximum of the valence band lies at the same K value, then we call this material as a direct band gap material or direct band gap semiconductor. Now, if the maximum of the valence band and the minima of the conduction band lies at the different K value, because x-axis is the K, then the transition will happen. Suppose we want to excite one electron from here, and then we want to excite this electron. So what will happen? The direct transition, how the direct transition will happen? So from here to here, but here the minimum energy is this one. So there is a change in the K also. So that is the reason for solar cells and for the absorption of the light at a maximum strength, we require direct band gap material. And that is the reason silicon is not the best choice for the solar cell fabrication. And this is the absorption of the different materials. So we can see that this is the absorption of silicon. So you see that this is increasing slowly. However, the direct band gap material like indium phosphide, copper indium selenide, their absorption, you see that it is kind of a vertical line. Okay, so that is the reason like silicon we required about 300 to 500 micrometer layer to absorb the total solar spectrum. However, the direct band gap material required only few hundreds of nanometer layer that can absorb the total spectrum and can generate the similar or better efficiency. And that is the reason actually there is always search for alternative to the silicon materials, where we can have the alternative materials about a few hundred nanometer of layer which can absorb the total solar spectrum and which are direct band gap in nature. Now, when we suppose here, this is the material, okay? Now, in a material, when we shine the light, and it creates electron and hole. Now, this electron and hole which were generated once this electron is here, so that is higher energy state for the electron. So if we do not separate this electron and hole at two different physical places, then what will happen? This electron will come and then recombine with the hole and generate the photon or heat, and that electron and hole will be lost. What we want, our purpose is that we want to separate these carriers away. So what we generally do, we create a p-n junction that is creating an inbuilt electric field inside, which is helping to separate these carriers. So we have the electron which is behaving like a mass particle, so which can easily go to the slope down. However, the holes behaves like a bubbles here. So the bubbles goes up. So the for the hose, the minimum energy is going in this way, in this direction. However, the electron minimize their energy going to the downhill direction. And then we have the electron accumulated this side and the hole accumulated in the p-type material. And then we have this negative terminal and positive terminal, and it behaves like a battery. So that's we want. So if you connect this into the external source, so what will happen? The electricity will flow into the outer circuit. So this is the basic working principle of solar cell. So now the question comes, how to absorb the maximum light from the sun and how to efficiently separate this electron and hole pair. Because I already mentioned that you have a photon, and this photon will excite this electron from valence band to the conduction band, right? So we do not want to lose this electron. We need to separate this electron at the different side, and the hole should be on the other side, so that they should not recombine each other. So these are the like research where how many electrons we are able to collect. Okay, so that will maximize the efficiency. Efficiency means, suppose we sign the 100 photons and we are able to collect 100 electron and hole pair at the end electrode. So that means efficiency is 100%. So this is the way actually we try to maximize the performance of the solar cell by using the research and development. So this is the basic solar cell. So you have seen this like silicon solar cell, and there these lines are the metallization lines, which is used to collect the electrons or the holes at the one end, and the other end we are try to collect the other type of the carrier. So when you shine the light, the electron and hole pair generated, they separate it at the two electrodes, and then it is acting like a battery, like this will be negative and positive. So whenever you are connecting a load, it is current flowing in the outer circuit, and then this is converting the sunlight into the electricity. The basic things actually here that is efficiently helping to create the electron and hole pair is this p-n junction. So we have the n and then p, and the light which is absorbed just near to the p-n junction, only this light or this electron hole pair is able to separate out. Otherwise, the light, if suppose absorbed somewhere here where the electron, there is no electric field. So what will happen? This electron will not able to diffuse up to this point because there is no electric field which will help this electron to drift here. So what will happen? This electron will, after its lifetime, it will recombine. So that is the reason, like we want to have the kind of a pin junction where the junction length you can increase, and then we can have the better and better separation of the charge carrier at the pn junction. So this is there are few fundamental points that we need to discuss here. So this is the short circuit current. What is short circuit current? So short circuit current is the maximum current that produced by the solar cell when the both terminals are shorted. Okay, so this is the maximum current, and that maximum current is depending on the band gap of the material. So if we, according to this criteria, we want to have the lower band gap, right? So that it can absorb all the solar spectrum. So this is the thing, you can see how much photon is coming per unit area, per unit time on the Earth surface. And this is the wavelength. So if I have the band gap around like 1100 nanometer corresponding to this one, which is silicon 1.1, then this material will absorb all solar spectrum on the left hand side from this. Okay, if I have the material which has band gap is corresponding to 500 nanometer, what will happen? This material will only absorb this radiation, which is very small. Most of the radiation that we have is in this visible region. visible and NIR region. So we should select the material which has the band gap in this region. But according to this short circuit current, we should have the as low band gap as possible. Okay, but the another parameter that we have is the open circuit voltage. Open circuit voltage is the maximum voltage that is generated by the solar cell when the both terminals are open. And according to this, we should have the maximum open circuit voltage. And to have the maximum open circuit voltage, we should have the higher band gap. Okay, so these two things actually are contradicting to each other because we want to have higher short circuit current and higher open circuit voltage. So there is always a sweet point, the maximum point. So we cannot have higher band gap, otherwise it will reduce the current, and we cannot have the lower band gap to maximize the current, then it will have the low open circuit voltage. So the maximum performance of the solar cell is generated if we have the band gap of about 1.4 electron volt. Okay, so these are the like characteristics of the solar cell. So we have this is the IV characteristic in the dark, and this is the IV characteristics in the light. So when we say that we have a solar cell which has this efficiency, so generally what we do, we shine the light, okay, that is equivalent to the solar light, that is called the artificial sun in the lab or solar simulator. We shine the light which has an intensity of 100 milliwatt per centimeter square. We shine that light on the solar cell and then we test it, how much the current and the voltage it is giving. So here, so this y-axis is the current, x-axis is the voltage. So this is the current. So the maximum current when the voltage is 0, okay, so this is the short circuit current, and when this is like open circuit voltage, the maximum voltage that we can get. So this is VOC. But the maximum operating point is when we have the maximum maximum point. So this is corresponding to JM and VM. So the efficiency of solar cell efficiency is P out, how much power we are getting, divided by the P in. So P in is the 100 watt milliwatt per centimeter square, which is fixed, the power coming from the sun. And then this is the ISC into VOC, okay, then multiply by the fill factor. So this is the efficiency that I am getting, okay. For ideal solar cell, sheet resistance should be 0. So that's this line should be vertical and shunt resistance should be infinity. That means this should be like this. So when you have the vertical line and this, then you will have the fill factor 100%. Okay. But the maximum fill factor is like you can get from the silicon or the other solar cell is about 80%. So I already mentioned that like you need to have the band gap nearly about 1.4 electron volt. So you can see that the silicon or this gallium arsenide that are actually is coming in that range. Okay, and this is because to maximize the or matching the materials band gap with the incident solar spectrum. So these are the different solar cell technology. So this is the first generation solar cell is monocrystalline or polycrystalline silicon solar cell. Okay, the second generation is the amorphous silicon because the people start to work on the amorphous silicon or hydrogenated silicon just to maximize the efficiency, so and minimize the cost. Or we can have CVT solar cell, which is also commercialized and is giving actually higher efficiency. Or we can have the copper, indium, gallium, sulfide and selenide solar cell, which is having efficiency more than 22%, which is also commercialized. And we also have the CGTS solar cell. So in that actually the amorphous is still not performing well, but CGT is having a problem of the cadmium and this element. However, this copper, indium, gallium. So here we have the indium and gallium, which is a bit expensive. Okay, so that's why I actually try to replace this indium and gallium by zinc and tin, so that we can have the cost-effective material for the large area production of the solar cell. The third generation solar cells are good, like perovskite solar cell. They are giving efficiency more than 25%. But the problem is the stability. Their stability is only few hundred hours, and you need to have fabrication inside the glove box, the nitrogen filled glove box. So that is the still actually the research is going on, and most probably let us see if you'll get something out from the perovskite solar cell. So here actually we are working on copper zinc tin sulfide and selenide solar cell. Why? Because this is earth abundant, high absorption coefficient, and because of this tight band gap material and a suitable band gap. Okay, it's about 1.4 electron volt, and you will have like a lot of solar cells. The people are trying to put that in the is kind of a panel outside, or you can have this like kind of a nature inspired design to have the solar spectrum sign on this. So these are all the different designs to maximize the or you can have this solar panels that is covered on this region, because you need to have the area also available. Okay, so in Rajasthan, people suggest that we can put this more and more panels in the Rajasthan, but the problem in the Rajasthan is different. We have this solar spectrum there is like about more than 300 days, but the problem is the sand. And once you this panel is covered with the sand, then what will happen? Their efficiency will drastically reduce. So that challenge actually is still there. You have to clean, and you cannot clean that panels every day with the water, or you have to find some alternative so that the dust should not stuck to the panels and should not stop or decrease the efficiency of the solar panel. Or people are working on the like flexible solar cell also. You can see here the flexible solar cell, and it's like you can put it everywhere. Now you yeah, different design is coming, like charging backpack where you can charge your mobiles and so on. So what we are working here in IIT Roper, so these are the facility that we have. Okay, so we this is the chamber where we can have the three sputtering guns. So basically we are working on physical vapor deposition of this copper zinc tin sulfide and selenide solar cell deposition. Okay, so we can fire all these three guns simultaneously. And here you can see that we have the two chambers which are interconnected, like this chamber and this chamber connecting through this load lock. And we can have this two guns, and here we have the three guns. And all these guns is used to deposit the entire solar cell. Now, what is happening? Like, I'll just go a little bit about the fundamental of a thin film deposition. So, in physical vapor deposition, what we are trying to do? So, in physical vapor deposition, we are trying to create the vapors of the material. Suppose I want to deposit molybdenum, or I want to deposit gold, or I want to deposit silver, and that is in the film form. So, film form actually is the thickness maybe about few hundred nanometer only. So how to deposit that film on the substrate? So I need to create the vapors of that material. And when we have the vapors, then these vapors I allow to condense them on the substrate. Okay, so you can see that the vapors we are creating creates the situation like a fog. Okay, so here in this fog, this water amount of the water content is more than it should be in the condition in the atmosphere at that particular temperature. And you have seen that when in the morning time we have the fog, but in the noon time this fog disappears. This is because the temperature increases. So this is temperature dependent. Now in the someday actually we have the fog in the entire day. So that means the amount of the water content in the ambient is much more than. So this is creating a situation, and this situation is called the supersaturation. And you have done like many experiment your schooling time, where you have a beaker and you are adding a sugar or salt, then this is disappear, you again put a one spoon, disappear again a spoon, then you will have some salt remaining at the bottom. What you do, you heat a little bit, about 50 degrees, 60 degree or 70 degree, then that salt or sugar will disappear. Now you add one more spoon, then what will happen? You have more solute that you are dissolving in the water or the solvent, that at room temperature. Now you cool down that liquid or the solution is the supersaturation, because the amount of solute that you dissolve or that amount of the solute that is there in the room temperature condition is much more than the amount it can sustain. So we required that supersaturation condition during the deposition. Okay, and then that is actually a little bit physics. So we can have this condensation, and that condensation, this is the Gibbs free energy, which tells you about the thermodynamics, whether this reaction will be feasible or not. And this is the diameter. So this is a particular diameter. You have that this is the barrier, and this is the Gibbs free energy. So this is the critical radius and the Gibbs free energy. But the message from there is that once these vapors are condensing on the substrate, then there will be form a nuclei, and nuclei is of the nanometer size, and then they grow to minimize their energy to form the complete layer. So what we do in the lab, so this is the we deposit layer by layer and by using the sputtering. So this is physical vapor deposition method. What we does here, so what is happening, like we have a target. Okay, so this is cathode material, and then this is the anode. So what is happening? So in the cathode, we generally keep a target. Okay, and when we have the target, we supply some argon or the inert gas, and that gas is filled inside, and we applied a high voltage. So what is happening? The electrons will emit from the cathode, and this electron will accelerate away from the target. Now, when this electron is going from this target to anode, they will collide with the argon atom, and then they will create the argon ion, which is of positive charge. And this argon atom will accelerate towards the cathode. And once they will accelerate, they will remove these atoms of the cathode. Okay, and then these atoms will be depositing here. Now this condition resembles just like a vapors, like we have the load of water vapors. So these vapors of this material will be there, and that will be condensed on the substrate here. That is how actually we are creating a thin films by using the plasma. So this, you can see that this is the live photo of the sputtering from the 3 different targets. So you can see that this is the target, and this is the substrate, and this is during the sputtering. So you can easily see that the plasma. So plasma, you know that, or fourth state of the matter, which has all possible electrons, ions, neutral atoms, and complex and light. And this is the system, and this is the complete structure of the solar cell, where we have the bottom electrode, and then again we have this moly, that is back contact. This is the main layer. This is the absorbing layer, which is absorbing the light and creating electron and hole pair. Now I told you that this electron hole pair need to be separated out. So we need a p-n junction. So this is the n-type layer, CDS. So this is the p-n junction, and this side we collect the electron. On the back side we collect the holes. So this is the complete fabrication. So we have the soda lined glass, and then we deposit about 800 nanometer of molybdenum film. On top of that, we grow about 1.5 micron of CGTS film. And then on top of that, we deposit 60 nanometer of CDS, which is N-type. And then we deposit transparent electrode. I told you that we are also working on transparent conducting oxide. So why we are working on this material? Because, and why these materials are important here? Because we are shining the light from top, from this side, right? So this side, this light should penetrate and reach up to this point where this light will be absorbed. And then this layer, this is the main layer, which will create the electron hole pair. And then this electron hole pair will be separated out at the interface. And the total thickness of this total active layer is less than the human hair thickness, which is about 80 micron. So you can imagine that the advantage of these direct band gap materials, where the silicon, the active layer thickness is about couple of like 300 to 500 micrometer. But here, the entire thickness you can add, okay, this is 1 micron, and the total is about 1.5 micron. That's it, or maximum 2 micron. The human hair is about 80 micron, 80 to 100 micron. So you can see that this is less thickness than the human hair. This is the state of the art. So this is the the institute where I did my postdoc. And this is to certify the efficiency throughout the world. So if you are claiming that you have created a new material, and then this material actually you are getting a world record efficiency, then you need to send this material here to get the efficiency certified. So you can see that they are collecting the data way back from 1975, even before that. And then up to 2022, this is showing how a particular technology is progressing. Okay. So you can see that for CIGS solar cell, the green solid dot is here. The efficiency is about 22.7. It is increased actually by 0.4. And this is the inorganic solar cell, which is CGTS. Okay. So this is here, and the efficiency is still about 12%. Now the question is like, why I just replaced two elements, indium and gallium by zinc and tin? So why the efficiency is not up to the mark? What are the reasons? So that was with these motives actually we started that project long back in about 2014 to 2015. So this is the structure of the solar cell. So we have the substrate, molybdenum absorbing layer, and then CDS layer, and then window. And this is how actually the efficiency of the solar cell is progressing. And up to like now, this efficiency is about 13%. However, for CIGS solar cell, the efficiency is more than 22%, which is already commercialized. So why there is a performance gap? To understand that, we have published many review articles from our group. So if you want to get more details, you can get from these articles, or you can request me, I'll send you. So what is the technological challenges? So major technological challenges is the narrow phase stability. So if you have like Cu2s, ZNS, and SNS2, their pure phase is only and only the size of the laser pointer here. Okay. Otherwise, if you go anywhere in this phase diagram, then you will find the off stoichiometric material. Okay. The second thing is the high amount of defects and secondary phases in the material. Okay, and that leads to the low open circuit voltage. So the low open circuit voltage here in this material is much smaller than the optical band gap of the material. So these two things are really a killing factor for the CGTS solar cells. So we have also compared what are the secondary phases in this solar cell. So we realize that this copper zinc tin sulfide, which is essential material, except that we also have zinc sulfide, which is insulating material, and Cu2s, which is kind of a conducting material, which is resulting the shortening of the device. Or we have SNS2, which is having N-type. So that means if we have the SNS2 and is forming in the absorbing layer, it is making a PN junction, which is creating a kind of recombination of the carriers or other different P-type materials. So we do not want to have all these secondary phases. The result of the secondary phases and defects are the fluctuation, the local fluctuation in the band gap, which is leading to the recombination of the carriers. And the recombination in the layman language, you can understand that if I assign the 100 photons and then 100 electron hole pair is generated, so 70 electron and hole pair is recombined because of these defects. Okay, so we only have 30 electrons and holes that is separated out. So that will drastically change the efficiency of these materials. However, in CIGS solar cell, you can see that there is no like the Bantel, the state here in between. However, in CGTS solar cell, there are so many defect states that is really affecting the open circuit voltage of the CGTS solar cell and are the limiting factors. So we try to recombine or combine all this data that is presented in the literature and then presented in the form of this review article that we published in 2020. So from here you can see that, so this is the band gap. Ideally, band gap and the open circuit voltage should be equal. Okay. And this is the activation energy. So that means if the activation energy and this is nearly equal, that means this side, so that means this is good. If we are getting a defect which is deeper into the band gap, so that means we will go in this direction, so that will act as a recombination center, and that will also affect the open circuit voltage in the solar cell. So how to deal with that? So there is a another article published in Science from the another group. So what they have suggested is, this is the y-axis and this is the x-axis, and this is the short circuit current normalized with the Shockley-Quasar limit, which is the theoretical limit for a single junction solar cell. Okay, and this is the open circuit voltage and the fill factor normalized with the SK limit. So, and it is divided into three different regions. This region, the reddish region, is the region where the solar cell achieve the efficiency less than 50% of their theoretical limit. The greenish region here, where we achieve the 50 to 75% of the efficiency of the theoretical limit. And here it's more than 75% of the theoretical limit. So you see that here all this crystalline silicon, gallium arsenide, and gallium indium phosphide, all these solar cell technology are here. And in this region are mature technologies. But CGTS is here. So that means how to increase the efficiency. So we can push this point in this direction, and that can be done by using the carrier management. So carrier management means we need to work on the defects, interfaces, and many more. So these are the different interfaces in CGTS solar cell. So you can see that in the interfaces, we have the back interface here. So that is the MOLI and CGTS. Okay. Or we can have the interface on the top, which is the CGTS and CDS. Okay, so these are the different interfaces which are really impacting the carriers recombination at the interfaces. Okay, so these band alignments and all these, like suppose at this interface, the formation of the molysulfide or molyselenide at this interface with the CDS really impact the band alignment. Okay, so you can see that this is CTS, and then this is the formation of molysulfide selenide, a very thin layer because of the diffusion of the sulfur and selenide at this interface. Or here, like diffusion of the cadmium into this interface. Okay, that is really impacting the performance of this solar cell. People are utilizing different strategy, like suppose I deposited one type of the layer on this side, like titanium nitride, or another layer that is just to stop the diffusion of the sulfur or selenium into that other side, and try to achieve the interface engineering and improve the carrier selection. So I would like to focus more actually what we are doing. Okay, so this is our result. So what try to do actually is just critically role of zinc sulfide, like zinc to tin ratio, to enhance the copper zinc to tin sulfide and selenide solar cell efficiency to minimize the secondary phases. So we generally, like, there are secondary phases, but we focus on the Cu2s because this is more conducting, and this is kind of segregated at the interface of CDS and copper zinc tin sulfide, and this is responsible for shortening the device. So we use this PVD technique, where we have the three targets like zinc sulfide, copper, and tin sulfide targets, which are being sputtered. Okay, and then making the three different layers. Okay, so these are the different parameters. You will find that all the details in the paper, but I just, for the sake of the student, so there are the three different samples and that we started, and then these are the power densities for the sputtering for the three different targets. And then what we have done, we have annealed that into S2SMB, and just to make it more stoichiometric to the sulfur point of view. And this is the cycle for the annealing. And these are the different characterization, like XRD and the Raman, just to confirm what if we have the secondary phases in the system. And you can see that the secondary phase is actually is changing, like Cu2s we have here. Okay, so all these three samples have the Cu2s, which is not required. So you can see that this particle that is segregated at the interface is the Cu2s. And now we are going to deposit cadmium sulfide and on top of this other layers. So what will happen? This device will never work because we have these bigger particles which are highly conducting in nature. So we have to first control them. Okay. So what we have done, we have just measured their composition. Okay, about their all composition, and we realized that this what is the good sample. Like we can start with this S01 to further optimize, and then we just further did work on our power density of the different targets, and you can see that this composition of this S05 is near to the good actually that we can work on. And this is the FWHM, like the XRD performance, and then this is the intensity of this CGTS to Cu2S. So you can see that there it is changing. Okay, so this is changing like here. So this is S5, and then the minimum FWHM means that the good performance. Okay, so this S05 actually is the good sample, and this is we propose the mechanism, and you can see that the Cu2S phase is almost eliminated from these samples, and this is only possible because to control the zinc to tin ratio, which is helping to make this intermediate compound like Cu2S-SNS3, which is acting further with this ZNS and making this CGTS. So if this reaction is not complete, then we have the unreacted Cu2S, which is coming here. Okay, so this is the region actually. And finally, we tested the device and we observed that the initial results show that efficiency is about 6 to 7%. So then what we have done, we start to tailor more actually towards the nano charge transport in this copper zinc tin sulfide and selenized solar cell. So this is this work is based on the nanoscale charge transport and local surface potential distribution in the silver doping. So what we have done, we try to dope the silver into CGTS. Why we try to incorporate silver? Because we want to minimize this anti-side defect CuZn. So what is happening actually? They are sitting in the position of other element, and the reason the problem for that is they are making a defect site, and with this defect site is creating a problem for the charge recombination. So what we want to replace the copper by silver so that their formation energy, this formation energy is high. Now they cannot form this anti-side defects. And how we can verify? We can verify by using the nanoscale characterization technique. So we try to dope the silver, more and more silver here, but we cannot keep adding the silver, because what will happen? The silver will increase its band gap. And we know that the optimum band gap is about 1.4 electron volt. So if we keep increasing the silver, then it will be off the optimum band gap. So we need to optimize the amount of the silver that we can dope in the CGTS. So these are the different characterization. And this is the main actually that we have done this nanoscale Kelvin force microscopy. Okay, so this is basic things like this is measuring the contact potential difference at nanoscale, or difference in the work function of the material, okay, at nanoscale. Because the work function of the tip we know, at nanoscale we are going and measuring the contact potential difference, which is nothing but the work function difference between the tip and sample. So this is you can see that with the different concentration of the silver adding, we have calculated the contact potential difference, and we measure that line profile at the grain and the grain boundary, and we observe that there is a difference in the grain and grain boundaries. In CGTS solar cell or all the solar cell, the minority charge carrier, which is electron, generally flows through the grain boundaries. If the defect are there, this electron will be captured. So we want to have these grain boundaries, okay, passivated. So that's how actually we try to include the silver into that. So these are the conducting at atomic force microscopy. So we again actually verified that yes, this optimum results for the sample is coming from one particular deposition. Okay, one particular composition of the silver into that, because it is optimizing the carrier passivation. And then we further actually did some more measurement, calculated the mobility of the carrier that is coming from the CSAFM. And we further actually verified to calculate the making this detector and just verify the on and off, like how if you shine the light, then how fast we can create and remove the charge carriers. That was also further confirmed by using this CGTS solar cell. So this is the I'll discuss about now actually alternative to the conventional CDS, because everything was taken from the copper, indium, gallium sulfide and selenide solar cell. So it may be possible that this cadmium sulfide, which is coming from this technology, may not be suitable for CGTS. And also the CDS, if you are talking about the CDS, is not having an optimum band gap. The band gap actually is about 2.5, 2.6 electron volt. So that means it will start to absorb the light. We want to have a material which allow all the solar radiation to reach to the active layer, so that the radiation will be absorbed in the copper, zinc, tin sulfide and selenide absorb the layer. So what we have done, we propose TiO2, okay, and we compare that what is the performance of TiO2, amorphous TiO2, in contrast to the conventional CDS. So these are the, like when we deposit TiO2 by using low power sputtering and this CDS by using chemical bar deposition, then we try to see what is the elemental composition at the interface. So this is TiO2 and then this is CGTS, and then what we have done by using the depth profiling by using the X-ray photoelectron spectroscopy. So we are removing layer by layer and measuring the elemental composition and their elemental chemical bonding, and then we have performed this XPS analysis with that. And we also calculated, so this is the Fermi level, okay, so the maximum, and then this negative side actually we have the valence band. So you can see that where the valence band lies. So we calculated that and we constituted the total band alignment of CGTS and TiO2, and we found that the TiO2 band alignment with CGTS is better than the CDS. And we also calculated this like the measurement here, okay, and we perform this Kelvin Profos microscopy on the CGTS and TiO2, and you can see that we have the huge contact potential difference at the interface. What is the advantage? The advantage of that is, like when we have the large contact potential difference here, so that will help us to separate the charge carriers from CGTS and at the interface. So this is the, like again we try to do the engineering of the grain boundaries, okay, in this CGTS, and that article actually appears on the cover page of this Journal of Applied Physics. So what we have done here, so since we know that we have the TiO2 and CGTS at this interface, so what we are trying to do actually, since this is oxide and it may also have the oxygen vacancies, what we have tried to do, we can control easily the oxygen vacancies in the TiO2 by controlling the oxygen partial pressure during the deposition. So we have deposited this TiO2 on top of CGTS under different oxygen ambient and try to map the surface and the junction mode potential. So what is the surface potential? Surface mode. So one of the contact is taken from the TiO2 and the AFM tip is on top of TiO2. So it will measure the like potential in plane. But if I take the one contact from TiO2 and another contact from bottom, so it will flow like this. Okay, so these are the two different mode that we have done, and then we measure on this and then calculated at the different oxygen partial pressure, and we observe that this oxygen is playing a critical role by annihilating these defects at the interface of this TiO2 and CGTS, and also oxygen is penetrating into the CGTS. I have not shown the results here. Yeah, it is like you can see that this oxygen is also penetrating. So this is the oxygen, this is penetrating in the CGTS, which is passivating the defects at the grain boundary of the CGTS layer. And this is actually some preliminary result of that. And this is the actually image that covers on paper on the page. So with this, I would like to conclude. So we have critically varies the zinc tin ratio, okay, without affecting the copper to zinc plus tin ratio, okay, to achieve the optimize the copper zinc tin sulfide solar cell. We successfully suppress this highly determinantal phase. This is Cu2s secondary phase, which is conducting in nature and responsible for the sorting of the CTS solar cell. And we applied this a unique nanoscale chemical-force microscopy to avoid this secondary secondary phases and defects like copper zinc antisite, and utilize the TiO2 as an alternative layer for the CTS solar cell. So this is the group. Really thankful to all my students. So uh, Kulvinder also graduated and Nistika is also graduated. So that is the work done by these two students. And these are the current students. So 6 PhD students are working, including 2 master students that is doing projects, and 5 students already graduated from the lab. So this is the work done by these students. I'm just representing on their behalf. And these are our collaborators. I would like to sincerely thank all the collaborators. And thank you very much. And thank you very much, Pragya, for inviting me, giving me that platform. I can share my results. And thank you, Dr. Amit, for this opportunity. So if you want to know more details about my lab, so you can please do scan that. And I'm also open for any collaboration. So student can send me email for any internship, or if you are interested to join my group. So with that, I would like to stop here, and thank you very much.
Thank you so much, sir, for this wonderful session. I believe that the participants must be enriched after attending your session. So now this session is open for questions and answers. Two persons have asked about something about Fermi energy or Fermi level. One
Yeah,
is
so it is just written there, just Fermi level, but I'm not. So you can allow the
yeah,
speaker,
yeah.
like the
I
audience,
should
to ask.
allow them to chat with you. Just a minute. So Shanmukharao Samantam, you can talk to the resource person. You are allowed.
Good afternoon, sir.
Yeah, good afternoon.
No, actually, I just replied to the question. I think it came into question answer session. So the one of the what you call attendees is actually asking what is
Vikram
EF.
Verma
Okay,
ji.
okay. What
He
is
So
had
I
EF?
asked.
just
Okay.
I just actually answered to that.
Okay, okay.
Holy
Okay, thank you, thank you, thank you.
Sir, Ms. Himani Chaudhary asked, wonderful session. How can we join your group, sir?
So it
And can
depends
we have the
actually
PPT of the session?
on what level you are. Are you a MSc student? Then please qualify the gate, and you are welcome. And if you qualified JRF, you are welcome to join anytime.
Sir, I have allowed her to talk to you if she has any specific question.
Yeah, yeah, please.
Thank you so much, sir, for unmuting me, and very good afternoon, sir. I'm a researcher in NJP Rohilkhand University. Currently, I'm pursuing my PhD over there,
Okay.
and my pre-course work is going on. And I'm really interested in working for the field of organic semiconductor. So, if you
Oh,
have any suggestion for me, so sir, please.
yeah, actually, I worked on organic solar cell like PTH, TPC, when all these, and this nanoscale charge transport. But I'm not actually I'm a physicist, so I do not work directly on this organic materials. So I worked on inorganic, all these materials for solar cells and photodetectors application. But Yeah, so on what materials you are working and what is your research area?
Actually, sir, it's pre-PhD work is going on, so I'm not quite
Okay,
comfort
okay, okay, okay.
decided till now. But I'm just searching. That's why I'm joining this seminars also. So if you
Okay.
can give me any suggestion for that, or any website or any mail ID for the further suggestion.
Actually, for this currently for solar cell, I can suggest you actually there's a high boom for perovskite solar cell, and but the perovskite solar cell actually that is required for some kind of a particular environment to grow. So that is actually is currently going on like all around the world for perovskite solar cell.
Okay, okay. Thank you so much, sir. Thank you so much.
Yeah, thank you.
Any participants having any other queries, please either raise your hands or you can drop your questions in the chat box. So till the time other participants are gathering their own questions, I had one query, sir.
Yeah, please.
As you in starting told that this indirect band gap semiconductor like silicon, that is not a very suitable candidate for consideration for solar cells. But
Yeah.
still, there is a lot of work going on in case of silicon-based solar cells. So, is there any specific reason, or there is anything which is highly motivating us to still work for the solar cell also, including this silicon?
Yeah, actually we already have the silicon, but silicon is not going to replace till we have some other mature technology. Right. Silicon solar cell is the lifetime. You see that they are claiming 25 years, but the panel once you have is not going anywhere for 50 years. Only the electrical contact and those things can degrade, but silicon, there's nothing happen. So there
It's
is
all about
no,
maturity of the technology, right?
yeah, we do not have still like the perovskite may have the chance actually because their efficiency is coming up to the point like 25, 26, in 27%. But that is on laboratory scale. But the challenge for the perovskite is the problem of the stability. It is only few hundred or maximum few thousand hours. We want to have the technology up to 25 years or at least 10 years. So that is the reason. That's why actually a lot of research is going on alternative materials. Silicon is very expensive. Silicon solar panel actually is not very cheap, very expensive. And because why I told that these are not the like good material because it's indirect band gap material. So we required 500 to 700 micrometer thickness. However, the direct band gap material, like you see that the thickness, total thickness is less than the thickness of the human hair. So that is the cost cutting.
Sir, Mr. Vikram Verma wants to talk to you.
Yeah, please.
Vikram Verma ji, you can talk to sir.
Good afternoon. Is I am audible?
Yeah.
Good afternoon, all of you. First of all, I really thankful to the Shri Vishnu Vidyapit Vishwavidhalaya for organizing such workshop for us, and it's really a really good experience. And hopefully, we are learning, and we are learning so much from the informative session, sir. And sir, one slide, sir, please, if you open, sir, comparison of champion solar cells, sir.
This one.
Back, sir, that one, sir. Sir, that one from the highest peak, sir. That from offer, sir. Sir,
Yeah.
from offer ISC, sorry, sir. Please some throw light, sir. Please some throw light on that, sir. If
Actually, these solar cell, these are the company name actually. So these companies or the institute name. So you see that NREL. So that means these are the points of the efficiency and which year it was invention, and these are the name of the company. So these are the name of the companies. But
okay.
single junction solar cell will only lead to like maximum up to 32%. As you know that this is the fundamental limit. But
Okay, sir.
you should ask the question like why it is showing up to 48%.
Right, sir.
Because this is not a single junction solar cell. This is a multi-junction solar cell.
Okay, got it, sir.
Yeah.
And one more thing, sir. If someone is doing PhD from other university and other anywhere, so someone is able to test their samples at IIT Ropar or not, sir? Is it possible or not, sir?
Yeah, we can test that, but I was showing this image because suppose you are saying that I have created a solar cell which is showing a world record efficiency, then we cannot certify. You need
Okay.
to send this solar cell to this institute, National Renewable Energy Laboratory, Colorado, Golden.
Okay.
They will certify. They will give you have seen that many research paper published with this logo, right?
Right, sir.
So that means they are certifying that the efficiency of the solar cell is this much. So these are the certifying agency in the world.
Okay, sir. And sir, what is the criteria to take the admission in the PhD, sir?
So this
Over
is
there.
either you should have the GATE qualified or NET JRF.
Okay, okay, got it, sir.
Yeah.
Thank you so much, sir.
Thank you, Mr. Vikram Varma. Sir, one more slide which you had shown about like two chambers were connected through a load lock system. So can you just give some kind of brief on that system?
This one?
Yeah, yes. What it is meant for.
Oh, this you want to know the details?
Yeah, about like why we are having two separate chambers and load
Okay,
lock, because
okay.
load lock generally we go for if we don't want to bring something out, and in situ only we want to do some two kind of processes.
Actually, so you see that here I have the substrate.
1, 2, 3 का लूंगा चल.
And then this is the contact. Actually, this is moly contact, right?
तुम्हारा हो
So what I want to have the maximum layer deposited inside. So this sample is transferred here and then it transferred to this chamber. Then I deposit this moly layer from this one of the target. I anneal this sample here and without exposing to the atmosphere, because I don't want to expose this layer to the atmosphere. Otherwise, what will happen? It will start to make a more moly oxide.
Yeah.
So without exposing, I will transfer that layer. So this rod actually is used to transfer, and then I will transfer this side. And what is my next layer is
CGTS.
So I deposit from these three. So I will deposit up to this point. After that, I do CDS. So I can bring that back and then I can deposit CDS from here. Or I can do the TiO2, which is one of the target here. And then once it is TiO2, then nothing is going to happen. It is oxide layer. And then after that, I will transfer to the another system, this one. Okay, so this nearby, and then I have one target is AgO, another target is zinc oxide. So I'll deposit all these three and then final metallization.
Okay, sir. Got it, sir. So in one go, the whole wrapper will be like a whole
Yeah.
system will be come manufactured itself. And everything
Yes.
will be deposited in one.
Yeah, yeah.
Thank you so much, sir. So, sir, now no more queries I am able to see. And I will share your contact, this email ID, so that if someone is having some query, he or she may ask.
Yeah, yeah, please. So the advertisement currently open for PhD. It is open for anyone. Please
Okay.
contact us. So if you are JRF qualified, you can come anytime. Just shoot an email. If you have GATE qualified, just there is a regular advertisement coming every 6 months. You just apply, and the ad is still open. In December, we are hiring, and I'm taking 2 more students this December.
So, sir, your Facebook profile or something, some link I will share with the candidates. They can.
Yeah. Please,
visit
LinkedIn.
me.
Actually, I'm like on LinkedIn or Facebook, or you can just scan this if somebody wants. That will leads you to the homepage. So the smartphone, you just scan it and it will lead you to the research page of our page.
Okay, sir. So now as we are coming to the end of the session, I invite Dr. Amit Saxena, convener of this FDP, to propose vote of thanks. Over to you, sir.
Thank you, Prikyaman. And this session was really a session of FDP. Students interacted a lot. And I think in the coming times, students will going to bother you, sir. They're going to contact for the admission PhD.
Sure, sure, sure.
So very, very nice. You started very fundamental. You started in such a way that somebody who is not aware about solar panels, solar cells, they can understand how they work and how they manufacture, synthesize. Really outstanding. Great talk for me also. Eventually, it is good for my participants also. So finally, on behalf of Shri Vaishnav Vidyapith Vishwavidyalaya and from the Department of Physics and SBIS, I put my heartily thanks to Mukesh Kumar sir, and I would put my thanks to all the participants who are here for a long time, and all the technical team, Pragya ma'am, Neetu ma'am, and my HOD too. Thank you very much, sir. Thank you, Mukesh sir. I will contact you sometime, and in fact, and discuss something more about perovskite solar cells.
Thank you.
Thank you, sir. Thank you.
Okay.
Okay, sir. Thank you, all of you. Now we may leave for today, and tomorrow again we will be meeting for the next session of the day. Thank you so much. Good day to all of you.
Thank you, Pragya.
Ji, sir.